I added a little discussion in the introduction here about why induction actually works. If any of you want to read about this, the important thing is this. The reason induction actually works is that the natural numbers are defined by induction. So we're getting closer and closer to the point where we need to have a conversation about what the real numbers are. So let's start by having a conversation about what the natural numbers actually are. And what the natural numbers are, I mean, if I go to MathLib documentation and I look up, please. Pretty please. Should I click it again? Why is this taking so long to load? Reload. Did I kill my, okay, there we go. We're inching. That's not supposed to take a long time. Okay, I'm gonna let that load while I talk over here. The reason induction works is because the very definition of the natural numbers is induction. The way the natural numbers are defined is that you declare out of nowhere that just natural numbers are some abstract thing. We're going to declare that there exists a natural number that's called zero. But I called it Alice. We called it zero. Okay, there is something called zero. That's all we're claiming. That's our foundations of the natural numbers. And then anytime you have a natural number, we can make another one called the successor of that number. And that's it. That is how the natural numbers are defined. Okay, with a zero and successor. From zero, you get one. By the way, do you know how natural numbers are defined? Let's see if this loads. Yeah, it loaded. So let's look at NAT. I just want to look at the actual definition in actual MathLib so that you see that I'm not, no, not class of NAT, just NAT. Here we go. NAT, the natural numbers. This is why the natural numbers start at zero. Zero is the additive identity. It's a number that you add to any natural number and doesn't change it. So zero is the smallest natural number. So that's, of course, there's all kinds of syntactic sugar that makes it possible for you to just write numbers. But when you write, so let me make a little notation here. In type theory, well, I'll just say in lean, when you write 4, let me not do 4, let me do 3. 3 is literally successor of the successor of the successor. Is that right? 0, 1, 2, 3. Yeah, of 0. That's what 3 is. In set theory, just to compare things, does anybody know what 0 is in set theory? Okay, 2 of you guys, 3 of you guys, 4 of you guys have seen this. 5, Sam, what is it? The empty set. Okay, and it has 0 elements. And what is 1? Joe? The set that contains the empty set. Okay, and that has 1 element, namely the empty set. And how about 2? It's a set that contains the set that contains the empty set. Sam?
So the empty set.
Why?
So that it has 2.
You wanted to have 2 elements. The size of this number 2 that we're defining needs to have 2 elements. Do we have 2 sets? Yes, we have 0 and 1. So it's a set that contains the empty set and the set that contains the set containing the empty set. Did I say too many contains there? Okay, thank you.
Famous thing, 1 is the set containing 0.
Yes, 1 is the set containing 0, 2 is the set containing 0 and 1. And 3 is the set containing 0, 1, and 2. So it contains the empty set, it contains the set that contains the empty set, and it contains the set that contains the empty set and the set that contains the empty set. And that's 3. Yeah, you can't tell which ones are open and closed. You can tell there's a little hook this way and a hook that way. That's pretty consistent, as bad as the handwriting is. Okay, but this is really bad. I mean, it's not really bad. It's how mathematics was done for a long, long time. But you see how many symbols I have to use as opposed to 0, successive sets. This, of course, is still very bad, right? Because it's not how you write numbers. You don't write numbers. 20,000 years ago, people wrote numbers on a bone. There was a bone, and the number was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20. And then eventually we figured out you could just write 20. And that was a lot easier than writing 1 20 times. But literally the way that the natural numbers are implemented is by induction, which is why the principle of induction works so well and so easily. within this dependent type theory foundation, okay? But literally what's happening under the hood is there's a number called 0, and then there's a successor, and that's it. And so the definition of the natural numbers is by induction, and that's, by the way, why 0 is a natural number, as much as it pains my earlier self to admit that.
What are the type of natural numbers? You need to prove that it works. Is that how it works?
So you need to define, for example, addition. What's an addition operation on the natural numbers? How do you define addition? Okay, this is getting way off topic, but off topic. How do you define n plus m? How do you define addition? So there's a function called add, which takes a natural number and another natural number and returns a natural number. And the way it's defined is as follows. By induction. It's defined by induction. If m is equal to 0, so the case that m is equal to 0, n plus 0 is defined to be n. And if m is the successor of some other m prime, then n plus m is defined to be the successor of n plus m prime, assuming you've already defined that. And then you can do all the operations from there. So if you guys want, there's another video game called the Natural Number Game, which builds all of this up from scratch. Natural Number Game. It's going to look a little familiar. Here's the Natural Number Game. And there's a tutorial, which will be very familiar to you guys. Then there's going to be Addition World. And the first thing I think you do in Addition World is, can you see this? You prove a theorem called zero add, which is that when you take 0 and you add it to a natural number, you get n. Didn't I just say that that's how it's defined? No. It was n plus 0. The fact that n plus 0 is n is one of the axioms. The fact that 0 plus n, we don't know that addition is commutative yet. This definition does not tell you that addition is commutative. You actually have to prove it. And so before you prove it, you have to prove that 0 plus n is n. And the way you're going to do it is by induction, because that's how the natural numbers are defined, okay? So we're not going to go into this because you're more than welcome to go and play that video game yourself. That video game is what motivated this video game. But just FYI, the reason induction works on the natural numbers is because the natural numbers are induction. There's no difference between natural numbers and induction. They're themselves defined by induction. And so any property you want to prove about that, induction is a natural avenue. Okay, good. Let's go. Let's go. Lecture 9, more on sequences. So we, at some point, have to start dealing with finite sums, and it's as good a time as any. So we're going to learn a whole bunch of stuff. Is this big enough for you guys in the back? Brandon, you can see it? Should I make it a little bigger? No, it's okay? All right, you guys have better eyesight then. We have a sequence A. We have a natural number n. What we're going to do is sum. So this notation, if I slide this, will it break everything? I can still see this, which is all I need to see right now. Okay, so let's discuss. Our theorem, which is not much of a theorem, we're given a sequence A. We're given a natural number n. And our goal is to show that for all n strictly less than n, if you sum k in range n, I'll explain what that is. What are we summing? I don't need a comma in natural language. I do in lean. If I sum ak, then that's an upper bound for a of n. Let's parse this. Range n means the numbers from 0 up to n minus 1. Why is that range n and not range n minus 1? Yes? How many terms are here? N terms. So it's a range on n terms, which means the sum of n strictly less than capital N, or k strictly less than capital N, okay? So k is going to range from 0 to n minus 1. We add up all of the first k terms of A, and I claim that that's no bigger, that's no smaller than the term an when n is less than capital N. This is blatantly obvious. I hope you agree. Yeah? We agree, bless you, that this is obvious? This is one of the terms, and then we're adding up a whole bunch of things, of which this is one. Okay, but of course, how do you actually prove that? So the proof will go by induction. By the way, we have our goal starts with for all n. Shouldn't we intro n? Note. Okay, I can make this full screen. We don't need to be looking at this anymore. Please, there we go. Note, goal starts with for all n. So shouldn't we start with intro little n hn? Joe. We need induction on capital N. This won't work if we induct on little n. It's not a statement about little n. It's a statement about capital N, about how many terms there are in the summation. Okay, so no need induction on capital N, not little n. I don't have to write the word little. I can just write a little n. Okay, so let's do this by induction. All right, so we're going to argue by induction on capital N. So what are our two sub-goal 1? Sub-goal 1. What's sub-goal 1? Yes, exactly. For all n less than 0, absolute value of an is less than or equal to a sum k in range 0, absolute value of ak. And what is sub-goal 2, just to get it on the board? Sub-goal 2, we have a new hypothesis. Let's call this the induction hypothesis, hn, that says, what does the induction hypothesis say? Ayman.
Less than n.
Yes.
An is less than.
Exactly right. Less than or equal to a sum as k goes from 0 to n minus 1 of ak. And the goal becomes,
With n plus 1.
yes, for all n less than n plus 1. A of n is less than or equal to a sum as k goes from 0 to, well, n minus 1 plus 1 of absolute value of ak. Everybody see that? How do we deal with sub-goal 1? Suhas.
That's like an implied statement for the first part is false.
Yes.
Means the whole statement is true.
Exactly right. So let's get the first part. So let's intro n hn. And now what is hn? Hn is the hypothesis that n is less than 0, and that's not possible. So then we just say contradiction. We're learning a new tactic. I guess I should put it here. One of the new tactics is contradiction. So contradiction is if your hypotheses already contain a contradiction, there's nothing to prove. And then contradiction. Lee knows that n less than 0 is impossible. Done. Okay. Would it work? So contradiction would not work if we didn't do the intro step first, because it's looking in the hypotheses. There's no contradiction in the hypotheses until we get one of the hypotheses to be a contradiction. Okay, sub-goal 2. All right, now what? Akil,
Yeah.
please.
Wouldn't a contradiction imply the goal is false?
No, a contradiction in the goal is very, very good question. So if you have P implies Q, then you're right that if you have not P, that doesn't help you. But if you have false, if false is one of your hypotheses, if you have a hypothesis called false, false implies anything. Okay, false will imply any property. if you can prove 0 equals 1 inside your theorem provers inside your formal system, you can prove the Riemann hypothesis. You can get $7 million. I guess $6 million because the Poincare conjecture is already solved. But you can collect all the 7 million. I mean, obviously, none of this makes any sense. But why does false imply anything? Jeffrey.
Well, I mean, if it's like an if-then statement, right? You need the first part to be true in order to like actually.
Yes. Yeah. Yeah, it's do you guys know about the contrapositive? You learned about the in 300 or something. The contrapositive is like the if you have P implies Q, so let's just do a little logic aside. P implies Q is equivalent to what's the contrapositive? Exactly. Not Q implies not P. Okay, so if you want to prove that false implies P, the contrapositive of that is not P implies not false. Not false is true. But true is always true. So it's very easy to prove this statement. Okay, so if you have false as one of the hypotheses, you can prove any statement you want. Does that make sense? All right, so we get this to be one of the hypotheses by intro, and then we just hit it with contradiction. That'll solve anything. Brandon.
I'm just making sure, is this what the term like vacuously true means?
Yes. Something is vacuously true if if it's true not because of what it is, but because if anything is true. You've gotten yourself into a situation where you can prove anything because you've wandered into a contradiction. Okay, so now our goal is to prove this. How are we going to do it? How do you think summation is defined? Somebody said, Suhas? Yeah, induction. Induction. So there's a theorem. That theorem is one of our new theorems. It's called sum range successor. There's a theorem so let's call this have F1, which is that if you sum K from 0, let me write it actually formally so that we can see it. K in range n plus 1. N plus 1 is sugar for the successor of n. It's just a nicer way to see successor of n. Absolute value of AK. This is equal to a sum K in range n of AK plus one more term, AN. That's the beauty of summing up to n minus 1, is that here's the only place where we have a plus 1. Okay, so this is a sum up to n minus 1, and then one more term. All right, so that's by apply, and the theorem was called sum range. We're summing over a range, and then we have the successor. Sum range sum. Okay, that makes sense? So now we know that this is the case. We're basically done. We have to break things into cases depending on whether AN is in this range, in which case we can apply the induction hypothesis, or AN is the last term, in which case we have this. But let's make sure we get all those positivity. You should break into cases at the last possible place because you don't want to have to repeat arguments that you're going to use again and again. So let's record that this sum is non-negative. So that has a name also, sum non-neg. Sum non-neg says if all the terms that you're summing are non-negative, then the sum itself is non-negative. Okay, so let's do I'll call it F3 because you'll see what we need in a second, which is the fact that the sum K in range N AK is non-negative. That's by apply sum non-neg. But first we need a proof that all of these terms are non-negative themselves. So let's call that F2. F2 is the fact that for all K in range N, for all K between 0 and N minus 1, the absolute value of AK is non-negative. That we can prove by bound. By bound. And then we'll send F2 into some non-neg, and that'll prove that. So far, so good? Everybody following? All right, once we have that, let's also record that AN is non-negative. So that's fact 4, is that AN, A capital N, is itself non-negative. That's again by bound. Bound knows that the absolute value is a non-negative function. And now let's break it into cases. Does that make sense? So far, so good? How do you break into cases? By cases. We can probably just call this hypothesis H. And what do we want to break it according to? Whether other than Suhas, other than Jeffrey, other than Ayman. All right, Akil, go ahead.
Lowercase n is less than.
Perfect. Okay, so we have two now sub-goals. Sub-goal 1, they still say the same thing. The goal has been and remains to be this. Before we have access to little n, okay, before we have access to little n, we have to intro. Okay, so let's intro little n and h little n. So now we have a little n. This didn't use little n, this didn't use little n, this didn't use little n, neither did this, but before we can break in cases, so it doesn't matter if you intro here or here, that's that commutes. So now we're going to break it into cases according to this. If this is the case, then what? John. Use the induction hypothesis. So if we specialize the induction hypothesis, H capital N, to what value of little n? Our little n. I need a proof that little n is less than capital N. That's our assumption, H. Then this will make Hn look like what? John? Hn, absolute value of AK. And what's our goal? Let's remember our goal at this point. So we did an intro on for all n and capital N. Our goal is this, that the sum, I guess, let's rewrite by F1. Let's rewrite by F1 so that we take this sum up to range n plus 1 and convert it into a sum of 2 ranges. That makes sense? So let's rewrite by F1. So the goal becomes to show that AN is at most a sum over K in range N, AK, plus the last term, AN. Okay, so what can we do at this point? Jeffrey.
Thing on the right is.
So we have H capital N, which says that AN is bounded by the sum. We want to prove that AN is bounded by the sum plus one more term, which we know is non-negative. Linearith. Linearith, we have to give it F4, and we have to give it Hn. Okay, makes sense? How about in the other case? In the other case, H says that it's not true that n is less than n, but we have another hypothesis called H little n. H little n is that it's true that n is less than n plus 1. Strictly less than n plus 1. So what fact do we know about n, little n? Akil. It's equal to capital N, and bound should do this. Bound should know that if you have it's not true that n is strictly less than n, but it is true that n is strictly less than n plus 1. The only thing left is that n is capital N. Okay, now what? Our goal still says this, but we know that little n is capital N. Ayman.
Notice it's in the gas stove, so it's.
Yeah. So let's tell Lean that this little n on the left is capital N. What is that?
No special.
Specialize is if this was a function. Rewrite. It's a rewrite, yeah. So let's rewrite F5. Let's rewrite by F5. And the goal will become, the new goal is that absolute value of a capital N. Do I have little n's anywhere else? No. Is less than or equal to a sum of the AKs plus AN. And the sum goes up to N. Jeffrey? Linearith on F3. This sum is non-negative, so it's linearith on F3. Linearith on F3. Make sense? Let's do it. Okay. Let's go back to here. From the beginning, oops. Okay, from the beginning, we're going to resist the temptation. We see a for all n. We're going to resist the temptation to intro. Do not intro. Induction. What's the syntax? It's induction prime on what variable? We only have one natural number floating around. Capital N, yep. With, I don't know, I keep the names the same, capital N and the induction hypothesis, H capital N. Okay, so we have two goals. One is what happens if n is 0, and the second goal is we have the induction hypothesis, and then what happens for n plus 1. Bless you. What should we do here? Brendan. Intro NHN. Now I know that n is a natural number, and I know that n is strictly less than 0. Contradiction. Out of falsehood, you can prove anything. Okay, intermediate goal solved. Our next goal is now we're running the induction hypothesis. Now we don't have to resist the urge. Give me the little n, intro little n, hn. All right, so we have a little n. We know that little n is less than n plus 1. Before we break into cases, let's prove everything that we might want to prove. So for example, let's try this have f1. So have f1 is going to say, have f1 says that this is equal to the same thing where you don't go up to n plus 1, you only go up to n, which really means you only go up to n minus 1. And then plus one more term at the end. Now here's a problem. If I say plus one more term at the end, I think the way the brackets is going to work is that these two things are going to be bracketed and be adding too many things. So I actually need to close the parenthesis here. It's like when I wrote this, how did you know to stop, not to sum AK plus AN every single time? You didn't, I just left a little bit more space. Okay, but really I should put parentheses to know that the summation symbol stops there and starts there. Okay, and what's the name of this theorem? If I apply, it's a sum over a range of things with the successor. Okay, so that's right here. Where was it? By apply some range suck. Apply some range successor. All right, so we have this F1, which is this. And then what do we do? Let's rewrite by F1. Okay, now we don't need F1 anymore. We've just said AN is at most this thing or that thing. Again, that's going to be a case split depending on the value of little n. But let's make sure we record all the non-negativity so we don't have to prove it twice. Once you case split, the second goal is sitting there with its hypotheses. So get all the hypotheses you need in before you start doing that. Okay, so let's do F2. So have F2, which is that for all k in the range up to n, it's true that the absolute value of AK is non-negative. That's just trivial. Bound will do it. Once we have that, we can make an F3, have F3, which is that this whole thing, I'll just write it out again, sum over k in range n AK, comma, a sub k. The comma is how it knows that now you're starting to say what what the thing is. This sum is non-negative. And that's by apply. Okay, everybody see what I'm doing? Am I going too fast? No. That's by apply sum non-negative. Sum non-neg. How do I know that each of the terms is non-negative? Each of the terms that I'm adding up is non-negative is F2. F2 says each of the terms I'm adding up is non-negative. All right, so now we've proved that this side is non-negative. Let's prove that the AN is non-negative. What was that, F4? Yeah, right there. Have F4 is that this is non-negative. That's by bound. Great. And now there's really nothing to do but split into cases. By cases, according to, here we'll call the hypothesis H, according to whether little n is less than capital N. All right, so we have two goals. We have an active goal and a goal 2. The goal 2 is if it's not true that little n is less than capital N, and the active goal is that little n is less than capital N. In this case, we can what can we do in this case? I've lost all of you. Akil and Brandon are the only ones who know what to do. Okay, Sam. Specialize, yeah, very good. Yeah, we just have to read. We don't have to figure it out again. We already figured it out once. Specialize the induction. We're going to apply the induction hypothesis. To what little n? That little n, do I have a proof that n is strictly less than n? Yes, that's exactly what I just assumed. And now I know this, and I need to prove this, which just amounts to adding an, and an is non-negative, so Linearith. Linearith, I need to know H capital N, and I need to know F4. And we're done. Intermediate goal solved. All right, let's see how do we prove this. It's not true that n is less than capital N, so let's call that F5. I guess I could continue copying over here. N, in fact, is equal to little n, and let's see if bound does it. Looks like it does. So we know that n is capital N. Let's stick that capital N right over here. How do we do that? Rewrite. Let's rewrite by F5. Okay, great. And now I think the only thing I have to feed in is the positivity of F3, nothing else, because I'm just adding a non-negative term to the same thing on both sides. So let's try linear arithmetic on, oops, not F4. It didn't do it. That's good that it didn't do it because it's not true if you use F4, but if you use F3, nah, what did I do? Did I break it? Wait, where are we? This is our active goal. I'm scared in the editor because it's not. Let me retry F5. Let me try rewriting this and maybe we'll get back on track. Okay. Linearith, that's another bug. Linearith with F3 with my clumsy fingers, and now we're done. Okay. Why would I go through the trouble of having you prove something as trivial as an is bounded by the sum of the terms from 0 to n minus 1, including one of those terms? There's a reason to this madness, and let's see what that reason is. Our goal is to prove that if a sequence converges to L and L is non-zero, then the sequence is bounded. And in your homework, you'll remove the hypothesis that L is non-zero. Okay, so let me write down the problem. What does it mean for a sequence to be bounded? A sequence is bounded. What happens if? What happens if L is 0 is that's a homework. I didn't want to break it into cases. There's no reason to do that. You can do that yourselves and learn about it. Okay, so a sequence is bounded if there is a positive number m so that an is bounded by m. And what we're going to prove is that if so let's talk about this in natural language first. Actually we don't even need. Here's the next fact that we want to prove. I'll just move it over here. theorem. If AN converges to L, then AN is bounded. The sequence AN is bounded. Okay, what does that mean? Definition, this is called seq bounded. You give me a sequence A, which is a map from the natural numbers to the reals. I'll give you true or false prop. Yes, it's bounded, or no, it's not bounded. What's a sequence that's not bounded? Jeffrey. A sub n equals n, right? So example, if you have a hypothesis on A, which says that for all n, A of n equals n, then it's not true that sequence bounded A. That's, in fact, that's a good, I'll add that to your homework. It's a good little exercise. Okay, it's not, you'll see immediately how to do it. Okay, what does it mean for a sequence to be bounded? It's a true or false statement. It's bounded if there exists some positive number m, so that for all n, A of n in absolute value is less than or equal to m. Quite simply. Okay, so that's what we're trying to prove. We've given ourselves a little extra definition of the boundedness of a sequence. And if you converge to L, then the sequence is bounded. Now I'm going to break this into two cases. One is we'll add a hypothesis on L that L is non-zero, so that we can apply a certain theorem that we proved last time, or maybe 2 times ago. All right, let's think about this. How are you going to do it? So here's your sequence. It's doing whatever it's doing. It's going to L. It's getting closer and closer to L. L is non-zero. Why is it bounded? So exactly right, Joe. We had a theorem we proved previously that a sequence converging to L, and if L is non-zero, it's eventually bounded. Let me remind you, we have a theorem here. Where's our list of theorems? Definitions, tactics, theorems, here we are. Eventually bounded of seq con. So if a sequence converges, we had already proved, there we go. Make it a little bit nicer. Right about, whatever. If a sequence has a limit, and that limit is not zero, this is where we're going to use that the limit's not zero, then eventually there's a capital N, so that after that point, the sequence is bounded by 2 times the limit. Okay, question, Daniel? No. Jeffrey, question? No. You guys just like to hold your hand right here, an inch from where your hand would go if you had a question. All right. We proved that, what was this called? Eventually bounded of seq conv or something. A sequence converges. Okay, what this took was the sequence. It took the limit. It took the fact that the sequence went to the limit. Let's just call that HA. HA of type A goes to L. And then it took the proof that L is not equal to 0, because this is not true if L is equal to 0, this theorem. And it says that there exists some value of n, so that for all n greater than n, AN is at most 2L. Clearly, that's not true if L is equal to 0. You can go to 0 without eventually being 0. But otherwise, it is true. Okay, so as long as L isn't 0, well, 2L is somewhere over here. And eventually, if you go to L, then there's some point, capital N, beyond which you are always below twice absolute value of L. L might be negative. But that's not what I'm asking. I'm asking, it looks like eventually bounded should do it, but it won't, because we need it to be true for all n. None of those are real hands.
Yeah.
Daniel.
So if there's an n such that eventually bounded, can't you take the middle of that n? There's only finitely many values of a before that.
Exactly. So how are we going to implement saying, okay, you have this, eventually you're bounded by 2L, and then what about these finitely many terms? You just take the worst one of them, take the max. But max is annoying, so we're going to be sloppy. Instead of max, we're going to add them all up. Okay. Jeffrey, you wanted to say something?
No, that was
That's what you're going to suggest. Exactly right. All right. So the idea, let's work at the level of ideas first. After at once n is greater than this capital N, use for your bound, use 2L, and before, just add them up. Okay, so our total upper bound should be, it would be max, but we don't like max. Max is annoying, so just add them. Make it even a worse upper bound.
I like.
The way max is implemented would require me to teach you some more things that the tactics don't seem to do a good job of seeing through. But summation is something that we anyway have floating around everywhere, which is why I'm replacing maxes with sums. Eventually, we're going to have to deal with maxes. We can't, we'll actually want upper bounds, good upper bounds eventually. Okay, so we'll come back to that. So our total bound is 2 times L plus this finite sum k in range n of the absolute value of ak. All right, so that should be the first line of our proof, because what we want is seek bounded. Seek bounded says there exists an m and that m is positive, so that this holds. So if our goal, in fact, maybe we should start by reminding ourselves of the definition. We should change the goal to be this. There exists an m so that for all n, an is less than or equal to m. That's what it means to be bounded. And so we have to specify what our bound capital M is. What should we use? Yeah, that thing. Use this big sum and a 2L. Yeah, you can do it either way. I'll put the 2L first, 2 times L, so that I don't have to worry about whether the 2L is included in the sum or not. Sum k in range n of absolute value ak. Okay, so the goal becomes two things. The goal becomes, first of all, to prove that 2 times L plus the sum is positive, and a second thing, which is that for all n, an is less than or equal to m. Not m, but 2L plus the sum. Sadik.
It's like a very minor detail, but is it necessary to include that m is greater than 0? Or can we just say there exists an m? Because the absolute value kind of implies it would be greater than or equal to 0, just like.
So you might, if you have the sequence an where the an's are all 0,
Yes.
then this is true with m equals 0. And you will see in later applications, we will need the fact that m is strictly positive. Now you could say, okay, if it's true for that m, you can replace m by m plus 1, and it's still true, but it's more things that we don't want to have to deal with.
What I'm saying is, do we even need to qualify m? We just say.
You don't,
Yeah,
but the only thing you'll get out of this is that m is at least 0.
okay, and you don't want m equals 0?
I don't want m to be 0. So I want to specify in the boundedness that m is actually positive.
Why don't you want it to be 0?
Because we're doing this boundedness for the next level, which is an application of this. And in that application, it's important that m is not equal to 0. But as stated, if I just stated boundedness as whatever m is, it could be that m is 0. You could be bounded with a bound exactly of 0. That's if and only if, in fact, that's another good exercise. I should be writing these down. You're bounded with m equals 0, if and only if you're exactly 0, the constant sequence 0. But I don't want to deal with that, please. Suhas.
Oh, yeah, I mean, yeah, I was just gonna say, like, like, you could just like drop the qualifier, and then when you want to use it, you could choose an m that it's good. That's not.
Yeah, or you could choose m to be m plus 1 or something.
Yeah.
That's another, there are lots of things that you could do if you wanted to avoid this. I think this is one of the easy ways to package what we want to do. So you're absolutely right. You don't have to include this if you don't want to. Just say there exists some M, and you can get from that information things about M. But let's just already have in our accessible the fact that this bound is going to be positive. Okay. All right. So this is our new goal, is to prove two things. We have an and. What do you do when you have to prove multiple things? Sean, yeah, let's split the ands. Okay, split ands. So now we have one sub goal that says 2 absolute value of L plus this summation is strictly positive. Now, maybe before we split the ands, maybe we want to record some things about these sums. Sean. No, the goal, if once you split ands, the goal, so our goal, I should have said this is a goal. This is something you can't do on Blackboard. Our goal, our sub goal, maybe I should say, our sub goal becomes this.
I just meant like when you do the use. Like,
when you do the use, yeah.
Like,
yes.
okay.
Yeah. Yeah. Not an implies. The goal is not that if this is yeah, the goal becomes an and. The goal becomes an and. Because there exists an M that's positive does not say there exists an M, and if M is positive, then this.
Oh.
It's that there exists an M and M that is positive, and this holds.
Okay.
Yeah, that's I'm very glad you asked that question, because it's a subtlety in the logic. It's not there exists an M, and if M happens to be positive, then something happens. That's the difference between a for all epsilon positive. For all, if you give me an epsilon and you give me the proof that it's positive, then I have to prove something. Here I'm saying there exists an epsilon, there exists an M, and that M is positive. I have to prove that for you, and I have to prove this other thing. So that's why it's an and not an implication. Thank you for that question. Okay, so our sub goal is this. Our other sub goal, just to record it, is going to be this. For all n, an is less than or equal to twice absolute value of L plus this summation of ak going up to capital N. Now, as you may imagine, we're going to want non-negativity of this summation, non-negativity of the absolute value of L. In fact, because L is not 0, we can get strict positivity, and that'll give us our strict positivity. And let's record that before we do the split, so we don't have to do it multiple times. All right, so let's record, have F1 is that this sum is non-negative, the sum on the AK by apply, and what was that theorem? Sum non-neg. Sum non-neg. Sum non-neg is going to want an input that all of the terms are non-zero. Last time we proved it explicitly. I'm going to start giving you more and more tricks with lean. If the proof was just by bound, then you can just put by bound here, and it'll figure it out. I'm going to start trying to save us as many steps as possible. So if you know that this is going to try to prove it using the positivity, and the positivity was proved just by bound, then just stick in by bound, and it'll do it for you. Okay, so we know the non-negativity of the sum of the AK. Let's also have F2, which is the positivity of the absolute value of L. And that's because of, anybody remember what that was called? Abs pos, the absolute value is positive. Abs pos of non-zero. Non-zero. And we need the fact that L is non-zero, which we called, do we give that a name? HL. HL is the fact that L is non-zero. HL. Okay, so we're armed with these two facts. We go into here. Why is this positive, strictly positive? Bound will probably do it. When you have linear, when you can do it by linear arithmetic, it's better to do it by linear arithmetic. Okay, so linearith combining what two things? The non-negativity of the sum, which is F1, and the strict positivity of L, and it'll figure out the factor of 2. Okay, so that'll handle that sub-goal. And how about our other sub-goal? So now we have this situation. Did we ever, hang on, where did we get our capital N from? We never used our eventually bounded. We forgot to get our eventually bounded. So let's do a have. Yeah, we don't know what to sum up to. Nobody stop me. We don't know what capital N to sum up to. Let's have an F0. F0 is that there exists a capital N, so that for all n greater than capital N, absolute value of an is at most 2 times L. And that's by apply this eventually bounded of seek conv. And then with this information, A, L, H, A, and A, L, and a few more things. Daniel.
After, or can you just like immediately just choose N1, H1?
Very good. Very good. So in fact, you don't need this have statement. If you know what the proof of this statement is, this statement says what I just wrote out. For pedagogical reasons, I encourage people to write it out, but you're absolutely right. You don't have to write this at all. You could just say choose N H capital N, and then colon equals, and then this thing. So Lee knows that this is an existential statement, and so it's going to let you choose from it. So you don't need to have an F0. Yeah, since I'm now getting to the point where I want to move the formalization along. No. So this eventually bounded is an existential statement. It says there exists an N. So that's a hypothesis. So we choose that N. Give me the N that comes out of this proof, together with the fact that for all N greater than N1, yada yada. Okay, so we needed that eventuality first. Now we have a sub-goal which says for all N, for all little n. What should we do with that? Intro little n. Okay. This is a good spot for a quiz. What is the current goal state? I'll try to keep track of it too. Current goal state. Okay, what are all of our assumptions? How do I show you everything that you need to see? Okay, if you need me to scroll anywhere while you take the quiz, let me know. This you? Please put your name on.
Is it the goal state of just the sum goal?
Exactly. The current goal state at this point, because we've already proved the first sub goal. So just the second sub goal is current goal state. There is only one goal at this point. So I'll just record a couple of things that are obvious. We have a sequence AN. We have a real number L. We have a hypothesis called HL, which is that L is not equal to 0. And then let's collect all the other things. So we don't have an F0, because Daniel told us we didn't have to. We do have a capital N. I shouldn't be helping, it's a quiz. I mean, you can help each other. Yeah. You can talk to one another. Give me a thumbs up when you're done. Give you like 1 more minute to think about it. Is that far enough? Let's do it together. We have natural numbers, capital N and also little n. What else do we have? Let's start collecting hypotheses. What does H capital N say? It comes from this eventually bounded, right? So Hn says for all n greater than n, absolute value of an is less than 2L. Okay, what else? We have F1. F1 is that the sum of the AKs is non-negative. We have F2, which is that L is strictly positive, in absolute value at least. And anything else? I think that's it for the assumptions. Did anybody find another assumption? I think that's it for the assumptions. And what's our goal? Yeah, it's this. Okay, good. Does that make sense? Did everybody get that? Did I miss something? Is there an assumption? Say it again. That what? Is there an assumption that? Ah, very good. Did we miss that? Yeah, we missed that. Thank you. HA is that C-clim. Thank you, AL. Extra credit for Iman. We missed it. Okay. Got it? Great. You can hand those over somewhere. Joe, you mind being the point man? All right. Okay, so how should we prove this? Daniel? Here's our goal. Why is it true? Sean? Included the cases depending on. Exactly. Okay, so by cases H, depending on if n is greater than or equal to n or not. If it is greater than, well, maybe I should do it the other way around. Let's say by cases depending on if n is less than capital N. If n is less than capital N, then why is this true? Then we have F, whatever this is, F3, which is that AN is bounded by the sum of the absolute value of AKs that goes up to n. This is by apply. Did we give that a name? That's the theorem we just proved. That theorem that we just proved has a name, and it's called term less than sum. Of course, LT is the wrong word. It should be LE, but too late now. Term LT sum. It's not strictly less than, it's less than or equal to. Okay? And then we're done because of I can't hear. Everybody's mumbling. Linearith, thank you. Linearith, if you take F3 and you put it, so this is bounded by that, and L is non-negative, so F together with F2, we're done. Okay, the other case is that H says it's not true that N is less than little n. So let's have H prime, which is that N is greater than or equal to little n by bound. Hopefully it'll figure that out. And now what? Specialize H capital N to this value of little n with H prime. And H prime will say that this is the bound. And now it's linearith on Hn together with the non-negativity, which is F1. Okay, let's do it. Any questions? This makes sense? Okay. From the top. Okay, let's have this F0. Oh, we're not going to have an F0. I have to slide so I can see what's there. Let's choose. So let me do the have F0 just for a second, and then I'll rewrite it. First of all, let's change. Let's change the goal to there exists an M bigger than 0, so that for all n, an is less than or equal to m. Again, that change is purely for us. Lean does not need to be reminded of the definition. It knows what the definition is. I'm just showing you that the goal used to be the sequence is bounded, and it turned into there exists a bound. In order to get a bound, I need to know at which point to stop. So I'll do it the slow way. Choose have F0, which is that there exists some capital N, so that for all n greater than capital N or equal to capital N, absolute value of an is less than or equal to 2 times the absolute value of L. And that's by apply this theorem called eventually bounded of seq conv that takes A and L. What else does it take? It takes the fact that A goes to L. It takes the fact that L is non-zero, which is AL. And I think that's all we have. Unknown identifier. So obviously I got the name wrong. Eventually bounded underscore of. Eventually bounded. Let's see. Do I eventually bounded? Can I retry? This is why it's good to have better conventions. All right. So we got our there exists an n, but let me retry this. And instead of doing all of this apply stuff, I'm just going to say, I know that that's what it says. So choose NHN from here. Oh, come on. I'm sorry, not colon equals. You choose using. Thinking of obtain. All right, so we jump straight to, we have a capital N, and we know that for all n greater than capital N, an is bounded by 2 times L. So far, so good. All right, next step. What was the next step? Is to use, let's use 2 times L for the tail, and for the beginning, just add up the initial terms. Oops. I did that. Okay. I meant backslash sum k in range capital N, absolute value of AK. All right, that's our upper bound. We have 2 things to prove. There's an and in between. So we should split ands. Before we split ands, let's record our, don't be too trigger happy to split. Whenever you have a case split, pause for a second and say, will I be making more work for myself proving things later? So let's record these 2 things. F1, have F1, which is that 0 is a lower bound for the sum of k in range n of absolute value of AK. That's by apply sum non-neg. And then I need a proof that each of the terms themselves is non-negative, but that's just stupid by bound. So we're getting a little bit faster. So we have that. And then let's also have F2 that L is the absolute value of L is strictly positive by apply abs pos of non-zero. And the non-zeroness is the hypothesis on L. Okay. So now we have those 2 inequalities. Now let's split the ends. lit ands. Very good. Why is this thing positive? That's Linnerith on F1 and F2. Good. Intermediate goal solved. Everybody with me? I'm not going too fast. Next one. Here's our new sub goal. And so we should start. Now we have a for all n. Let's intro that little n. And now we're going to break it into cases. By cases, according to whether n is less than capital N or not. If n is less than capital N, then let's have F3, which is that absolute value of an is less than or equal to sum k in range n of absolute value of ak, and that's by apply. We called that, I can't even read my own handwriting, term LT sum. And what do you have to feed term LT sum? I think you just have to feed it A. All it takes is a sequence and a capital N. It takes a sequence and a capital N to know when to stop. Okay? So that's this upper bound. And we're adding L, which is non-negative, so it's just Linnerith on F2 and F3, right? F2 and F3 are the two terms that come together to give us that bound. Very good. Another intermediate goal solved. Our final goal, we know that it's not true that n is less than n, so let's have H prime that n is actually lower bounded by capital N. Bound should do that. Very good. And finally, I guess not finally yet, we have this H capital N. So let's specialize H capital N, 2 little n together with H prime. And now we know that an is bounded by 2L, and so now it's Linnerith on Hn together with the non-negativity of this thing, which is F1. What happened? Something isn't right. Why aren't I getting a message that everything was solved?
I think after you, then you need to 5,000.
Usually a 5,000.
Okay, please. Pretty please. God. Here we go. Okay, reloading. Aha, it's this thing, term LT sum. So term LT sum, let's just look at it. It needs an A. Oh, it also needs a little n. It needs an A, it needs a sequence, it needs the little n. I see. It needs a capital N, it needs a little n, and it needs a proof that little n is less than capital N. That's exactly H. Okay, there we go. Now we got it. Okay, next. Here's the thing we were actually supposed to do today. Our big boss. And this is the last of these sequential operations. Then we're going to get into some real stuff. Here's the big boss. No, I won't leave this for homework, but we can spend 8 minutes on it. We have sequences A, B, and C, and real numbers L and M. L is non-zero, M is non-zero. A goes to L, B goes to M. C is the product of A and B. Why does C go to the product of L and M? All right, let's write this down and talk about it. Obviously, we don't have time today to finish it. So here's our theorem. This is prod lim. If you take a product of sequences, the limit is the product of the. So we have an converging to L, and L is non-zero. Of course, the non-zero-ness of L is not essential. We have Bn converging to M, and M is non-zero. We have Cn equals An times Bn pointwise, and the goal is to show that Cn converges to L times N. All right, let's jump right to it. Let's talk about the mathematics. So let's try to prove this in natural language, and then next time we'll prove it formally. How do you do something like this? John.
I don't know this is right, but I have some kind of thought where CN is eventually within like epsilon, so we need to specialize fact that A and epsilon square root of epsilon.
Exactly. So so let's find out. So we have Cn is an times Bn, and we need to show that that's within epsilon of Lm, L times m. This is the key thing that we're going to need after we unfold definitions and move through all kinds of stuff. Where are we going to get this from? Roger, you got an idea? Oh, what was your idea?
How about the end of the CN approaches alpha seven?
Yes.
What if we take the log of all these?
Okay, so now you want to prove that logs that the log of a sequence has the limit, which is the log of the limit.
Yeah, but like that's logs.
We're going to prove a much better theorem than all of these theorems in I was going to say next time, but soon, very soon, that any continuous operation is something that limits pass through. Like it's almost the definition of limits is that they pass through continuous operations, or almost the definition of continuity that limits pass through them. But yeah, I like the thought, but it's begging the question because now we have to prove something else instead of just proving this directly. Sean?
I don't really if you add and subtract L times Bn,
Yes. Why?
because that way you can bound Bn, like, once you split it up with triangle inequality, you can bound, like, it becomes like epsilon plus epsilon, and then both of the terms attached to that line can be bounded based on the two lengths.
Exactly right. The idea is there's too many things changing at once. An is moving and Bn is moving, and we've changed both of them. And it's very hard to keep track when you change two things at once. Let's only change one thing at a time. So let me subtract off, what did you say, Bn times L? And add back in Bn times L. Okay, that's going to be a ring operation. That's bounded. Let's use the triangle inequality by An. So this is, I'll group these together and I'll group these together. And this has an L in common and this has a Bn in common. So this is bounded by Bn times An minus L. And this is bounded by L, I guess, absolute value of L times Bn minus M. And we need to make both of these things smaller than epsilon. Now, Bn, how big does Bn get? Daniel? Eventually, it's no bigger than 2 come in. That's true. And we could use that eventuality. Yeah, well, we proved a nice theorem that if a sequence converges, then it's bounded, period. So just use that. So this is, Bn is bounded regardless of what n is. It's true. We could have just used the eventuality, the eventual version of this and just made little n even a little bit larger if need be. But this is bounded by, I don't know, we have L's and M's, so let me use a K. Okay, this I can make less than any epsilon 1 by taking n large enough. I don't know what epsilon 1 is yet. How about L? Well, L is L. L is equal to L. And how about this? I can make less than epsilon 2. What should I make epsilon 1? Jeffrey. Perfect. Perfect. Now we know the whole proof. Okay, you see that? So if two things are moving at once, separate them. Make only one thing change at a time. We could have used the eventual version. Instead, we proved the boundedness across everything. So we have that boundedness. And then, do you think I can let you work on this by yourselves? Or should we go alone? No, okay, fine. We'll go over this together next time. All right, should we make, we have 1 minute left. Should we say a little bit more about what we're going to do? I guess it's clear. If we want to prove this equality, so we intro epsilon and h epsilon, that epsilon's positive. Now we know what to do, so we're going to make we need to get this K, so obtain a K from the boundedness of Hn. We'll need to prove the positivity of L, so that you see, we can't make this epsilon 2 if we don't know that L is not equal to 0. But if L is 0, then it's an even simpler argument. So I'll add all of these once we prove this theorem. We'll remove these conditions that L is not equal to 0 and that M is not equal to 0. But this is just the first pass through the theorem, and you'll break everything into cases and quote this or reprove it on your own. All right, to be continued.